remind me, what was our answer we got for this average speed right here? 39 point, what was it? 493. Okay. Now, if I had been going 39 in a 35, or even if you rounded up to a 40, if I had been going 40 in a 35, I probably would not have gotten pulled over, right? I was speeding, but not by much. They probably would not have gotten me for that. But that was my average speed for the whole trip. Whenever the cop pointed the radar gun at the truck and I was going too fast, this was a long time ago. I didn't have a minivan back then. Minivan's so much better. But I was going a lot faster than that. Now, if at the top I had tried to say, look, I have been 7,530 feet in 130 seconds, officer, so my average speed was 39 miles per hour. Is he going to care? No, he is not, right? So, average speed over that period of time doesn't care. What the cop cares about is your instantaneous speed at that point. Because now I guess they could get you with your average speed if they're like radioing ahead or something like, or something crazy like that, but they're not going to do that. This radar gun is what they're going to use. If we go back over here to the graph, let's think about another way that we could have done this. So we are looking right here, and we want to know the speed at that point. So this one actually has a few options for how you could estimate this. So we had talked about what we really want, since we want the speed at that point. What we could think about doing is trying to draw in like a tangent line, a line that just barely touches right there at that single point. And we could find maybe the slope of that line. Now, we don't actually have numbers for any of those, but what you should notice right here is in this little section right here, that tangent line looks awfully close just to the line itself, right? The points that we have on that line. It's not exact, because if we could draw a perfect tangent line, it would just touch at one single point. But it's awfully close to those points around it. So what we can do for our estimate here, is we want to know the speed right here exactly at 20. So we could find the slope around that. So we could use maybe 10 and 20, those 2 points, or we could use 20 and 30, or we could use 10 and 30 as our times that we're going to look at. Actually, if this were on the AP exam, because they do give questions like this occasionally, asking you to estimate, if this were on the AP exam, any of those 3 options would be valid. So you could find either this little slope of this section, or you could find this little slope of this section right here, or you could find the slope of that section from 10 to 30. Any 3 of those would be acceptable estimates for this. So I'm not going to do all 3 just for the sake of time. Let's just do the one between 10 and 30. So I've got the point 10 seconds, 450 feet. And then my other point I'm going to use is 30 seconds, 1,440 feet. So this slope is going to be a little bit different, right? Because we're not starting at 0 this time. With the other ones, we were starting at 0, so we just saw how far we had gone and divided how long it was. So we're looking at the change in distance over the change in time. So that would be 1,440 minus 450. You guys remember doing that y2 minus y1 over x2 minus x1. So we got 1440 minus 450 over 30 minus 10. So this is going to give me 990 feet over 20 seconds. And like we had to do on the other problems, we got to convert this. So we got 3,600 seconds over 1 hour. We got 5,000. Oh, wait, no, wrong side. That needs to go on the bottom. Feet is on top, so we need feet to go on bottom and miles to go on top. So 5,280 feet, 1 mile. And so if we grab the calculator, oh, I should have had you guys get your calculators. Everybody go grab your calculator. We need to do it at the beginning, and soon you will have. They have. Miss Billings told me they ordered the calculators yesterday, so hopefully next week I'll have them to pass out. But go ahead and grab your calculator for today. I should have told you guys to do that. You guys did put your phones up. That was lovely, though. Most everybody. Just 21. Alright, let's see. Yes. Oh, somebody got 6. Yeah, there's a list up there, Reagan. Reagan stole it, Liam. Alright, so if we convert that to miles per hour, so take that 990 over 20, multiply it by 3,600 over 1 and 1 over 5,280, I'm getting 33.75. And I'm going to use this squiggly equal sign here. The squiggly equal sign means approximately, so it is good. You don't necessarily have to use that whenever you are estimating, but it is a good idea to put the squiggly equal sign whenever you're estimating, because we cannot say that the speed is certainly 33.75, but it's approximately 33.75. Which is a little faster than we got whenever we did that average from 0 to 20, right? Because from 0 to 20, at the beginning we were going slow, but then we sped up. All right, so knowing what we know now, if I want to know the speed at 65 seconds, so 65 would fall right here between 60 and 70, okay? So right there between, if I want to know that speed at that point, if I think back over here to the graph, if we're looking at 65, we're thinking right here. Now in this case, there is a clear points that you should use. 65 falls right between the point at 60 and the point at 70 that we do know, right? So we're looking at that little segment of the graph. So if we find the slope here, that's going to be the closest we can get to the speed at that point. If we, you can see, if we just do how far we've been divided by 65, we're finding the slope of that red line I just drew in, the slope of like the average speed over that time, which is going to not be quite as steep as that little purple line that I have right there. So let's do that here. So again, it's like we've got the point 60, 3,380, and 70, 4,130. So slope formula will just be 4130 minus 3380 over 70 minus 60. So we are going to get 4,130,380. And so we get 7 50 feet over 10 seconds, which is 75 feet per second if you wanted to go ahead and divide, just because that's easy to divide. But that's feet per second. So just like we did on the last, we got 75 feet per second. We need to convert that. So seconds are on bottom here. We'll go on top here. Changing it to hours. And then feet are on top here. They need to go on bottom here. So we're changing that to miles. 1 mile is 5,280 feet. So we grab the calculator. 75 times 3,600 over 1, but I'm going to type that in, times 1 over 5,280 is going to give us 51.136. Which, unfortunately, is how fast I was going through there at that time. Or about. It could, again, I could have used that squiggly equal sign there if I wanted. This is the estimate of our time speed. Okay, questions? Okay, you can see, like, if I had done average, first of all, I wouldn't know exactly what number that is, but let's say we use that 4,130. 4,130 divided by 70. That would have only given me 59 feet per second, which if I multiply that by 3,600 over 5,280, that'll convert it for me. And, oh no, oh, that's because I didn't multiply by 59. And that would be only 40 miles per hour, even at that point. So, again, if only they had looked at my average speed, I wouldn't be in trouble, but they didn't. So, let's continue. So, on our next slide, we've got the difference between average rate of change and instantaneous rate of change. So, our average rate of change is going to be the change in the dependent variable which is your y, over the change in the independent variable, which is most typically your x, right? So it's a change in a variable over the change in the independent variable over a period of time. That's really important. An average rate of change has to be over a period of time. So it might be the first 20 seconds or the first 30 seconds. But it has to be over an interval. An instantaneous rate of change is different. It is the rate of change at one given I'm just going to call it x value, but independent variable if I was being more precise. It can be. And we can think of it as slope or rate of change of the tangent. Okay. Now, as far as a formula to do that, I can't really give that to you right now because you don't know enough, right? We're going to learn it, but that's calculus. There's a difference between average rate of change is something that we can use to estimate. Instantaneous rate of change, we cannot yet, because we don't know calculus yet, but we're about to. All right, so let's look at another application of this, and I don't know if we have time to do this or not, but we're going to do it anyway because it's really cool. So if we get a little behind, the other stuff I want to do should not take us long, and we can do it tomorrow if we've got to. All right, so this video is about, oh no, that's, the spider can go 0 to 97 kilometers per hour in 2.5 seconds. So the graph above gives the speed, f of t, in kilometers per hour of the car in t seconds. So a lot of times on questions that you're going to get, they're not going to label the axis, or axes, but they have told you what they stand for. What goes on this, what we would normally call the x-axis, but is labeled the t-axis here? That is seconds. Okay? What goes on the, what we would normally call the y-axis, but it's labeled f of t here? Kilometers per hour. So this graph is different than the other ones we've been looking at because it's got speed on that vertical axis, not distance like we've been looking at so far. So that is going to change how you're going to answer these questions. So I want you to look at the questions that are here, and I'm going to give you a few minutes to try them on your own. We'll talk about what the answers are on that.